Hello, everybody. Thank you for joining me today. So we're going to start with chapter 5, which has to do with probability distributions. And so have you ever wondered how the IRS detects fraud on a tax return? We're going to talk about that today. You're going to be able to figure that out by the end of this lesson. So let's actually start off with making a list of deductions. So let's suppose that, maybe let's make a name for someone. I don't know, I always like using the name Roger. If I could name all my dogs Roger, I would. So let's suppose that, we have someone named Roger and he made a list of all these claimed deductions. And we're gonna use a method to figure out if he is committing fraud. And we're going to use techniques that we actually learn in chapter 2. In chapter 2, we learned about frequency distributions and relative frequency distributions. So hopefully you all remember that. Okay, so we're going to go ahead and look at this list of claimed deductions, and we're going to organize it in a relative frequency distribution that is here on step 2. Okay. So stay tuned to figure out, hey, how does the IRS detect fraud? Okay, so notice how Roger has all these tax deductions. What we're gonna do is we're going to look at the first digit of all of these amounts. And so like for example, for this first amount here, the first digit is 1. For the second amount here, the first digit is 4. Okay, so what we're going to be looking is we're going to be creating a relative frequency distribution based off the first number or the first digit of all of these amounts. And so I'm going to go ahead and highlight them. You can do that on your paper as well if you want to follow along. And so I'm going to go ahead and highlight it for all of the amounts. We're just looking at the first digit, and then we're going to organize and figure out, well, how many values start with a 1? How many values start with a 2? How many values start with a 3, 4, and so on, right? So notice how I already started it for us on this side. Okay, so for example, we're gonna have four values that start with the digit 1. Let me show you which ones they are. Here's 1, here's 2, here's 3, and here's 4. Okay, so there are 4 numbers that start with the 1. All right, let's go ahead and look at how many of these amounts start with the 2 on the first digit. All right, so here is 1 and 2 and 3 and 4. So there are 4 amounts that start with the digit 2. I'm gonna go ahead and write that down here for us. Okay. And then we're going to look for how many start with the digit 3. So we have 1 and we have 2. So we only have 2 amounts that start with the digit 3. Hopefully you're getting the hang of this. Okay. If not, make sure that you write a little question on the side, like, so you can ask me later, where did I get this value if you're still confused. Now we're going to go and look for which amounts start with the digit 5. And so we have 1, 2, 3, 4. So it looks like we have 4 that start with a 5. Okay, we have 3 that start with a 6. We have 5 that start with the 7. And we are missing one more. We're looking for how many of these amounts start with an 8. So we have 1 there. Is that it? And 2. We have 2 amounts that start with an 8. Okay, I'm going to go ahead and write that down. And what we're going to do next is we're going to go ahead and find the relative frequency. So hopefully you remember that in order for us to find the relative frequency for each of my classes in this case, see I have Notice that I have 9 classes here. We're going to take the frequency and divide it by the total number of values that we have. And so we actually had 30 deductions here. And so in order for us to find the relative frequency of the first of all the numbers that have the digit of 1, we're going to have 4. We're going to do 4 divided by 30, which is approximately 0.133. Okay. Or if we want to write as a percent, 13.3%. All right. We're going to go ahead and do that for the rest of these values here. And so for the second one, we have 2 divided by 30. It seems like I believe we have more. Oops, I think I messed up here. Hold on a second. Let me check for 2 because it seems like on my notes I have more values that start with the 2. So I might have miscounted. So there's 1, there's 2, there's 3, there's 4. Okay, so we have actually 4 amounts that start with the 2. So I might have just written it wrong. So these two have the same relative frequency because they occur the same amount of times. Is approximately 0.133. So it looks like on my notes that we only have 2 amounts that start with the 3. So let me go back and look. I wonder if like I said something and then I wrote the something else, which happens. So here's one value that one amount that starts with the 3. Here's another amount that starts with the 3. And it looks like that is it. So I apologize for my little typos here. This should be a 2 because there's only 2 amounts that start with a 3. So I apologize, that might have confused you. Why was I writing what a 2 and then a 3? I think I was saying a 3 and then I wrote a 3 even though I meant to. Okay. All right, let's move on. So we have this is going to be 2 divided by 30, and that's going to be approximately 0.067. And then we have 3 divided by 30, which is equal to 0.10. It seems like I'm rounding to 3 decimals, so I'll just do 0.100. And then for the next one, it's 4 out of 30, which we already calculated. And this is approximately 0.133. So hopefully this is a nice little review of chapter 2, relative frequency distributions. And then 3 divided by 30, which is going to be equal to 0.100 if we round it to 3 decimals. And then 5 divided by 30 is approximately 0.167. And then 2 divided by 30, we already calculated that earlier, and this is approximately 0.067. And then the last one is 3 divided by 30, which is equal to 0.100 since we're rounding to 3 decimals. All right, so I want to make sure that you understand what these relative frequencies mean. So again, this value tells you that 13.3% of my amounts start with the 1. Okay, this value here tells me that if we write this as a percent, let me go ahead and write that as a percent. 6.7%. So this value here tells me that 6.7% of my data values start with a digit of 3. I want to make sure that you guys understand what these values actually mean in relation to what we're working on. Okay, so again, we are trying to see if Roger has created fraud in his tax return. Okay, and so we're looking at the amounts that he claimed as deductions, and we're gonna go ahead and use statistical methods to figure out, hey, is something happening? Is there suspicious activity there with Roger? So let's go ahead and turn to the next page. This is step number 3. We're actually gonna compare the relative frequency that we just found, which is also known as a probability distribution here. We're going to compare That one, this is the one that we just calculated. I just wrote all of them here for us for Roger's tax returns. We're going to compare that to something that's called Benford's law. And what Benford's law tells us is that if we have a set that is naturally occurring, like in real life. So for example, stock prices, population numbers, death rates, sports statistics, TikTok likes, financial and tax information, those are naturally occurring data sets. It says that if we have some of those data sets, that each number, each of the values, it's telling us that 30.1% of my values are going to start with the 1. Okay, and that's here represented right here. Okay, so Benford's law tells us that if we have a naturally occurring data set, let's talk about TikTok likes. Okay, that's a naturally reoccurring set. So that one, it says that 30.1%, if we convert this into a percent, 30.1% of the likes in TikTok are gonna start with the 1. That 17.6% of TikTok likes are going to start with the 2. And again, this could be actually 2 or 20 or 2,000 or 20,000. It just, that's how many amount of likes are going to start with the 2. All right. It tells us, Benford's law tells us that 12.5% of my data values start with a 3. My data values are going to start with a 9. So notice how these are actually decreasing. The relative frequency is decreasing. The probability is getting smaller every time as the number gets bigger. Hopefully you notice that. As the first digit of my amount increases, the relative frequency or the probability is going to be decreasing. The probability that it occurs should be less. And so we're going to go ahead and use Benford's law to check if Roger created fraud. If there is some suspicious activity with his tax return deduction. All right, so let's go ahead and look at the amount. So again, these values are the values that we got from the first page. All I did was just type them up for us so that they're nice and we can compare them. Okay. All right, so again, based on Benford's law, 30.1% of my data values should start with the 1. Look at Rogers. In Rogers' tax returns, all those amounts that he wrote down, he listed as deductions, 13.3% start with the 1. So that one is a little suspicious already. Okay, it's like 1/3 of the amount that it should be. So that's a little sus. Okay, let's go ahead and check the other one. Okay, well, for the amounts that start with a digit of 2, it's not too off. It's not too off. So maybe I'll just like, okay, that I'll let that one slide. And then for the values that start with a digit of 3, that one seems a little bit suspicious right there. That's like half of the amount. So this one is 12.5% and this one's 6.6%. So that's a little suspicious. This one, if we round, that one's almost a 1. So this one's okay. This one is almost double, right? So 7.9% and then 13.3% is not exactly double, but it's like almost double. So yeah, let's go ahead and claim that as a little suspicious. And then this one here, that one is a little suspicious too. That amount. This one's definitely suspicious. This one, Benford's law tells us that 5.8% of my data value should start with the 7, and in Rogers' list, 16.7% started with a 7. So that's almost 3 times the amount, right? Or the percentage. The percentage increased by 3 times. So that one's definitely very suspicious. This one, not so much. They're not that off. This one's suspicious as well, okay? Because this is 4.6%, and this is 10%. Okay. So what do you all think? Okay. Using Benford's law, we can detect if people are committing fraud. Why does that happen? Or what do people normally do that makes them be suspicious? So, what happens here is that when people make up numbers, they tend to make the first digit approximately uniformly distributed. So, let's go back to these numbers here. So they're going to make up a lot of numbers that start with the 1, or a lot of numbers that start with the 4, or a lot of numbers that start with the 6. Okay, so they're going to have a lot of values that, end up showing up a lot of the same amount of times. Okay, so that's why we can see that here in the relative frequency, there's a good amount of numbers that happen to be about the same, that come up about the same amount of times. Okay, so hopefully you found that interesting. Okay. Now you can detect fraud, as a tax person. It's like, hey, your numbers look a little suspicious. You should probably check that because you don't want to be messing with the IRS. Okay. So again, I said when people make up numbers, then they tend to make the first digit approximately uniformly distributed. All right. So yeah, look into Benford's law. It's really interesting. So it's not just for the first digit. There are also some rules for the second digit as well, what that second value should be, in the amount, and what should be for the third value as well. So, I recommend looking into that. It's really interesting. But we just use probability. We just use techniques that we have talked about in the previous classes to be able to detect fraud. So hopefully that was exciting for you all. So again, that is my introduction of probability distributions, which is the same thing as a relative frequency distribution that we talked about in chapter 2. All right. Okay. So before we actually talk a little bit more about probability distributions, I want to make sure that I talk about what random variables are and give you some examples of random variables. So a random variable is considered to be a numerical outcome of a probability experiment. Some examples of that is the number that comes up when you roll a die. So when you roll a die, it could be a 1, a 2, a 3, a 4, a 5, a 6. Okay. So again, a random variable is just, a value that comes up when you toss a die, a random value. Here, the height of a randomly chosen college student. Okay, so again, it's just, a height, it's a numerical outcome. Uh, and again, it's chosen here at random. The number of siblings a randomly chosen person has. Okay, so for example, if I was the chosen person, well, I actually have 4 siblings. Okay, so that value 4 would be considered my random variable, whatever this outcome is. The amount of electricity used to light a randomly chosen classroom. That's also a example of a random variable. And so random variables are actually going to split up into 2 different variables. And so we're going to have discrete variables and we're going to have continuous variables. Let me go ahead and draw a little diagram here just to make sure that you understand that it splits into 2 different types for all of my visual learners out there, because that's me too. Okay, so if we have random variables, a random variable could be discrete. It could be a discrete random variable. It could be a discrete random variable, or it could be a continuous random variable. Okay. All right. Well, let's actually determine like what is the definition of a discrete random variable and talk about some of those examples as well. So if we have a discrete random variable, these are going to be random variables whose possible values can actually be listed. The list may be infinite, for example, the list of whole numbers, but you can list them. So the list of whole numbers would be 1, 2, 3, 4, 5, 6, 7, right? They actually do go off to infinity, but we can list them if those were the values that would come out. So that would be our discrete discrete random variable. So for example, the number of vehicles owned by a family, that could be 0, that could be 1, that could be 2, that could be 3, that can be 4. Notice that all of these values, we can actually list them, okay? And they're normally going to be whole numbers. Not all the time, but they can, they're mostly going to be whole numbers. Another example is the number of cars sold at a dealership in a given month. It could be 0, it could be 1, it could be 2, it could be 3, it could be 20, it could be 30. But again, we can actually order those, or we can actually list all of those possibilities. Another example is the number of tosses of a coin before getting heads. Okay, so we can toss a coin, and then maybe we don't get heads on the same one the first time, so that would be or here's the number of tosses of a coin before getting heads. So maybe we toss it and no heads, we toss it again, no heads, right? Toss it again, no heads. Okay, so like for example, maybe it took us 3 times before getting head on a coin. So that's what the number of tosses of a coin before getting heads, that's what that means. All right, so again, they're usually going to be whole numbers, not necessarily, but they're if they are decimals, they should be nice decimals that we can still list, like 1.1, 1.2, 1.3, 3.2, 3, so they have to be nice numbers in order for us to be able to list them if they're going to be discrete random variables. Another example here of a discrete random variable would be the number of pets a family owns. Right? You can own 1 pet, you can own 2 pets, you can own 19 pets. So that's another example of a discrete random variable. So the number of pets a family owns. Another example would be the number of children in kinder, maybe in the kinder class. Okay. Uh, and for a continuous random variable, go ahead and fill that out. So continuous random variables are going to be variables that can take any value in an interval. Okay, so the possible values of a continuous variable are not restricted to any list. So for example, let's suppose that we're looking at the interval between 0 and 1. We can list, a continuous random variable can take any value between, any a value between any interval. So if we're looking at this interval from 0 to 1, and we can have values that look like 0.01 or 0.001 or 0.011, right? Or 0.0101. Notice that these are going to be really hard to list. Okay, so when it gets a little bit more complicated, when it's a little bit hard to list, that's going to be a continuous random variable. And so, for example, it's usually going to be like measurements or lengths. So length of a room, okay? Just because like, when you're finding the length of the room, it's possible that that value could be somewhere in the interval. So let's say that it's like, the room is, it's somewhere between 5 to 6 feet, somewhere, and so we have to like look through that interval and try to figure out like what is that value, right? What's that value exactly? And so it's going to be some value within that interval. So the length of a room is considered a continuous random variable. Measure the time it takes a student selected at random to register for the fall. In a study of weight gained by college students in the freshman year, researchers record the amount of weight gained by randomly selected students. The other one would be the height of students in a statistics class. That's an example of a continuous random variable. Uh, Also, the time it takes for a satellite to orbit Earth, so time as well, especially when we have like, milliseconds and stuff. So again, the time it takes for a satellite to orbit Earth. So let's move on to the next page. Now that you guys hopefully understand the difference between discrete and continuous random variables. Okay, so let's go ahead and talk about some of the qualities of a probability distribution. If you want to see an example, just look at what we just did, right? Um, this table here, all right, this is an example of probability distribution, right? We can talk about these as probabilities or relative frequencies. Okay, so what are those? What are some of the properties of probability distributions? A probability distribution for a discrete random variable, it specifies the probability for each possible value of the random variable. Like I said, we've already talked about this. Relative frequency distributions are probability distributions. And so some of the requirements that it has to have in order for us to have a probability distribution is that the probabilities always have to be between 0 and 1 inclusively. So again, it can be 0, it can be 1. The other thing about a probability distribution is that the sum of all of the probabilities has to be equal to 1. Now, if this is if we're written in as a decimal, if my probability is written as a decimal, but if my probability is written as a percent, then this would be between 0 and 100%. And if we sum up all the probabilities, it should add up to 100%. If probabilities are written as a percent, then the sum of the probabilities are going to equal 100%. Okay. So again, it just depends. But normally when we do the relative frequency distribution or a probability distribution, we're normally going to have them as a decimal. But again, I always talk about them in class as a percentage because people can relate more, with percentages than with proportions. But okay, so based off these requirements here that the probabilities have to be between 0 and 1, and that the sum of all the probabilities have to equal 1, let's go ahead and make sure that we understand those requirements with the tables below. Let's go ahead and see which ones of these represent a probability distribution. So let's look at the first one. Okay. We're not looking at these values. Okay. That's not what we're looking at. We're looking at the probabilities here. We're looking to see that all of these satisfy these conditions here. So we're not looking at these values. We're looking at these values here, the probabilities. Okay. Let's look at number one. So the first one, uh, does it satisfy both of these conditions? Well, let's go ahead and see. This value is between 0 and 1. Yes. Oh, we have a problem. That value right there is not between 0 and 1, right? It's actually a negative value. A probability is always a positive value that's between 0 and 1 inclusively. So this one's going to be, this is going to cause a problem here, this value. Let's go ahead and write that down just to make sure that we're all okay. So for table A, it is not a probability distribution because the probability that x is equal to 3 is equal to negative 0.30. Right? So the probability that x is equal to 3, right, that my random variable is equal to 3, this is the probability, negative 0.30. And we cannot have a negative probability. It's not satisfying this right here, right? It's not satisfying this requirement there. So as long as it fails one requirement, it is not a probability distribution. So let's look at the next table here. This is between 0 and 1, 0 and 1, 0 and 1, 0 and 1, 0 and 1. It satisfies the first requirement, but now let's make sure that it satisfies the second requirement, that if we add up all these probabilities, that it's equal to 1. This actually does end up summing up to 1. So let's make sure that we write that down. This is an example of a probability distribution because each individual probability is between 0 and 1 inclusively, and the sum of all probabilities sum up to 1. Okay, so now let's go ahead and look at table 3 here. Okay, do you all see the problem right away? We can see that one of the probabilities is already more than 1, right? So we already can exclude that. That does not represent a probability distribution. So is not a probability distribution because one of the probabilities is more than 1. So not only is that going to, not only does it not satisfy that requirement, but also it's going to also increase the sum of all of them, right? Again, as long as it fails one, it's not a probability distribution anymore. Okay, so let's look at this last one here. So far, this one, all of these values are between 0 and 1 inclusively. Let's go ahead and make sure that the sum of all of these is equal to 1. I can already see a problem because these two here pretty close, right? That's going to be 99, and then we still have 20 point. So this is 0.99, and then with these, that's already going to be 0.27. So we can already just, we don't even have to use a calculator here. We can already look at it and see that it's going to actually be more than 1. So that's going to be a problem there. So again, so I forgot to note here that that was the problem here. But this one here, the sum of all of those was actually, it was more than 1. Let's go ahead and write that down. This is not an example of a probability distribution because the sum of all probabilities is more than 1. Okay, so hopefully this activity helps you understand what the requirements are. Okay, so whenever we create a relative frequency distribution or a probability distribution, they're the same thing. We want to make sure that all the probabilities are between 0 and 1 inclusively, and then if we add up all the probabilities, that it equals to 1. Okay, let's go on to the next activity here. And so when we actually have probability distributions, we can actually find the mean of those probability distributions and also the standard deviation of them. And so here is the little formula for both of those. I know it looks intimidating, but trust me, they are okay. And I will show you at the bottom, I'm going to show you how it's not frightening. It's totally doable. You can also use technology to be able to find the mean of a probability distribution and the standard deviation or probability distribution. What this formula is telling me is go ahead and multiply your discrete random variable, whatever that outcome is, which in this case, and let's say it's represented by x, and multiply it by its respective probability. And then you're gonna go ahead and sum them all up. So that's what this is telling us here to do. And mu here, my mean, is also called the expected value of x. What is x expected to be? Well, we can just, that's the same thing as finding the mean, all right? So let me go ahead and highlight it for you just in case. All right, so again, mu is also called the expected value of x. Okay, what is x expected to be? Well, let's just find the mean of that probability distribution. Okay, so in order for us to find the standard deviation, well, it's a little bit more involved. We're actually going to take the random variable, subtract it by the mean, square that value, multiply it by its respective probability, and then add up all those values up. Okay, and trust me, like I said, you're gonna be okay. And I just want to remind you that this symbol is called sigma, and we use it to denote the sum. Okay, that's why I also wrote it down right here just in case. So again, x is the value of a random variable, p of x is the probability of that random variable, and the symbol, the Greek symbol for sigma is denoting the sum. Okay, so let's go ahead and look at a probability distribution and use that to find the mean and the standard deviation. Right, so let's suppose here we have an example. Let's go ahead and ignore all of this. Let me just go ahead and zoom so we can talk about like what kind of table, what is this table telling us? Okay, so here, this table here, x is the number of vehicles owned. Okay, this is our discrete random variable. And so x can be 0, x could be 1, x could be 2, x could be 3, x could be 4. So again, these numbers here represent the number of vehicles owned. And these values here are our probability. So this probability here is telling us that 23.5% of the people in Moreno Valley own one car. Okay, so I just want to make sure that you understand like what that table is telling us. Okay. And again, this symbol here is telling us, hey, take the sum of all of the probabilities. Because remember, we want to make sure that this here is actually a probability distribution. So the first thing that we need to do is make sure that all of these are between 0 and 1 inclusively. Check, all of these are between 0 and 1. And now we have to make sure that these add up to 1. So let's go ahead and sum all of these up. You can use a calculator. And yes, all of those sum up to 1. So good. Okay, so this here is an example of a probability distribution. So let's now go ahead and use this formula that we had up here to be able to find the mean or the expected value of the number of vehicles. Okay, so what is the expected number of vehicles in this city? So let's go ahead and find that, which is our mean. And then let's go ahead and use this formula to find the standard deviation. The reason why again, like I said, you're not gonna have to do this by hand, but I just want you to understand like what is technology doing in the background for you. Okay, so technology in the background is using these steps to be able to help you find the mean and the standard deviation. So I want you to appreciate your calculators or your technology here. But let's go ahead and try this out. So the first step here is what we're at. So at the very top of this table, I'm telling you exactly what we're gonna do in order for us to get these values here that to get all of these values. And I already found some for you. Okay, so that way we can move on a little bit faster. Okay, so here we go. So this part here is telling you multiply whatever your x is, your number of vehicles for that row, and multiply by its respective probability. So for example, in this first part here, okay, we're on the first row. My x is 0. The probability that there's no vehicles is 0.015. So I'm going to go ahead and multiply those together to get this value here. So again, that's how I'm going to get that value, and I'm just going to show you. I'm going to go ahead and do the steps just so that you can see what we're doing here. And this is just going to be 0 because 0 times anything is just 0. Okay, so again, that's how I'm going to get this value here. This value should just be 0. Okay, does that make sense? So we're using X, which is the number of vehicles owned. So for this row, we have 0. And then this respective probability, the probability of getting 0 is 0.015. We multiply those together. That's what this means, multiplying, and we get 0. That's the same thing I did to get this one, right? 1 times 0.2235 is 0.235. So now we're going to go ahead and do that for the next one. So we're going to do 2 times 0.425, and that's actually going to give us the value 0.85. 3 times 0.245 is this value here, 0.735. And at the end, 4 times 0.080 is going to give us the value of 0.32. Okay, and so let's go back to our formula. Our formula was telling us to do exactly that, to multiply the discrete random variable by its probability, and then we're going to have to sum it all up. And so that's what this symbol here is doing. At the end, at the bottom, we're going to go ahead and add these up, and that's going to be my mean, which is the expected value of the number of vehicles in this example. I'm going to go ahead and add them up, and this ends up being 2.14. I'm just going to leave it as round to 2 decimals here. Okay, so what this is telling me is, in terms of cars, right, the expected value of cars in this town is going to be 2. And that makes sense because that's actually what the highest probability is there, right? Most of the families there, let's say in Moreno Valley, they seem like they have 2 vehicles, because that's the highest probability. So the expected value, it makes sense for it to be 2.14. Most of the families own 2 vehicles. Now let's go ahead and find the standard deviation. So what we need to do is we're going to break this up into 3 different steps. So we first are going to do this inner part, and then we're going to go ahead and square it. And that's what we're going to do here. Right? Once we find this value, we're going to go ahead and square it. And then once we find this value here, we're going to multiply it by its respective probability. And that's what this step here is telling us. And then at the end, we're going to sum them all up. We're going to sum these values up. And then we're going to take the square root. And we're going to be able to find the standard deviation. Okay, so let's go ahead and do that. We know that the mean is 2.14. Okay, so here, in order for us to find this value here, we're going to find x, right, for the x for that particular row. So here, my x here is 0, my number of vehicles. And then I'm going to subtract that by mu, which is 2.14. So we're going to do 0 minus 2.14, and it's going to end up being negative 2.14. Right? The way that we got this value here was, again, finding our x here. Our x is the number of vehicles. For this row is 1. And then we're going to do 1 minus our mu, which is our mean. And that's 2.14, which gives us negative 1.14. Okay, so just hopefully you're still with me. And then my x is 2 in this row. My mean is, so we're going to do 2 minus 2.14, which gives us negative 0.214. Negative 0.14. And again, I got that by doing 2 minus 2.14. All right, the last one here, we're going to do, my x is 4. So 4 minus my mu, which is 2.14. And that's going to end up giving me 1.86. So let me go ahead and put that down. All right. Now the next part was to, once we found x minus mu, which are all these values, all these values are x minus mu, we're going to go ahead and take this value that we just found in this row, in this column, and then we're going to go ahead and square it. So if we take negative 2.14 and we square it, we get this value. We're going to go ahead and do that to all of these. So we're going to go ahead and square that value, square this value, and that's going to give us this one, square this value, square this value. Okay, so that's what this is telling us to do. So again, we're just doing step by step. So this is going to be 1.29, and this ends up being 0.74 when we square it. All right. Now the last step is, well, second to last step here is now we found, again, we found x minus mu, and then we found x minus mu and we squared it. And now we're going to multiply this value here by its probability, by its corresponding probability. So we're going to go ahead and take 4.58 and multiply by its corresponding probability, which is 0.015. And that's going to give us this value here. The next one, we're going to do 1.29, and then we're going to multiply it by its corresponding probability, which is 0.235, and we're going to get 0.306. For this last part here, again, we're going to take 0.020. Look at the corresponding probability for that row. It's 0.425. We're going to multiply those together, and that's going to give us this value, which ends up being 0.009. To get the last one, we're going to go ahead and take 3.460, multiply by the probability, which is 0.080, and that's going to give us this value here. So notice that your calculator does a lot of work on, in the back end. So so when we multiply those together, 0.277, right? And the last thing here that we're going to do for this table here is where we're going to go ahead and sum up all of these values here. And we already found all these values are these, right? All of, whatever the outcome was for that expression there. When we add all of these up, we end up getting the value 0.842. And then we're going to use this value in a little bit to be able to find the standard deviation. Okay, so let's go ahead and do the parts down here, just to make sure that we're understanding everything. Okay, so it's asking us, A is asking us, the average number of cars a family in a small town owns is, well, we know that we found that, right? We know that the average here, the mean or the expected value is 2.14. That's what the mean, what the mean is. And now it's asking us, what is the standard deviation? Okay, well, remember, the standard deviation is the square root of this number that we found. Right? Because again, remember, this number here is equal to this formula here. And so here, this is the same formula there. So now we found that value by using that formula. And now we have to take the square root in order for actually to find the standard deviation. I'm gonna go ahead and go over here. And so again, my standard deviation, my symbol here is sigma, and this is equal to the square root of the sum of quantity x minus mu squared times the probability, the corresponding probability. And we've already found that value that's in the radical, which is the radicand. And so this is going to be the square root of 0.842, which ends up being equal to, or approximately, 0.917 cars. Because remember, we're talking about cars here. Okay, so the average or the expected value is 2.14 cars. Again, the value, because we're talking about cars, it makes sense for just to round to 2, but we're just going to leave it for the purposes of the next calculation. Okay, so 2.14, and then my standard deviation is 0.917 cars. Okay. Now, part C is asking us, is owning 4 cars a significantly high number of cars? All right, well, let's use the range rule of thumb. And if you all remember, in order for you to be a significant value or an unusual value, you have to be 2 standard deviations away. And in this case, because we want to talk about a significantly high value, we have to be 2 standard deviations away above the mean. Okay, so 2 standard deviations above the mean. Well, what does that look like? Let's go ahead and write that down. So we have, I always like drawing a number line. I feel like it helps visually to understand what we're doing. So this is the mean, okay? In order for you to be a significantly high number or significantly unusually, an unusually high number, you need to be two standard deviations away or more. So mu plus 2 sigma is going to actually find you the value that is exactly 2 standard deviations above the mean. And so again, any value that is 2 standard deviations away or above is considered to be significantly high. Okay, so again, this is any value here. All right, well, let's go ahead and calculate. Let's go ahead and figure out what is this value and then see if 4 is greater than that value, right? Because if 4 is greater than this value here, then we'll know that 4 is considered to be significantly high. But if 4 is less than this value, then we'll know it's not significantly high. Okay, so let's go ahead and find mu plus 2 sigma. So we're going to find mu plus 2 sigma. And so that's going to equal to 2.14 plus 0.917. And this is going to equal to 3.057. A value that is 2 standard deviations above the mean would be 3.057. So this value here is 3.057. Well, the value of 4 would definitely be more than 3.057. So it would be in this area over here. And so 4 is here. I'm gonna want to make sure that I, highlight that that's what we're talking about. This is that same 4 here. Okay, so yes, now based on the range rule of thumb here, 4 is a significantly high value because it is above 2 standard deviations away, right? It has to be 2 standard deviations away or above that. Okay, so yes, owning 4 cars would be, you can say unusual or significantly high. I hope that makes sense. Okay, the last question here says, what is the probability that a selected family owns more than 2 vehicles? Owning more than 2 vehicles means that you own 3 vehicles, right? Or 4 vehicles. And remember, we just talked about probability in chapter 4. That keyword, that word or is hinting that we're going to be using addition. The probability that x, here x, remember x represents the number of vehicles, that x is more than 2 is equal to the probability that x is equal to 3, right? That x, remember the number of vehicles is 3 vehicles, that the family owns 3 vehicles, or the number of vehicles is equal to 4. And the reason why I'm stopping at 4 is because that is where my table stops, right? In this town, let's suppose it's a town in Moreno Valley, the most that people own is 4 cars. So that's why I stopped right here. If this table went up to 10, then I would stop at 10 because, more than 2 would be all of those up to 10. Right? But again, my table or in my town, there's only people own the maximum that they own is 4. And so again, that's why I'm stopping there. Okay, so remember, or is addition. And so we're gonna go ahead and use our probability rules to find this probability. So we're gonna look for the probability that x is equal to 3 plus the probability that x is equal to 4. And so we can all just use the table. So notice that my table here tells me that the probability that x is equal to 3, that the number, that people own 3 vehicles is 0.245. So I'm going to go ahead and replace that there. And then the probability that people own 4 vehicles, that x is equal to 4, is this probability here, 0.080. So we're going to go ahead and write those down here so that we can find this probability. It is equal to 0.245 plus 0.080. This is going to equal to 0.325. So the probability that a selected family owns more than 2 vehicles in Moreno Valley, let's suppose, right, it's going to be 32.5%. Let me write that down for all of us. So the probability that a selected family owns more than two vehicles is 0.325 or 32.5%. So again, if you have any questions, if if I lost you at any point, please make sure, you put like a little post-it note saying check with professor, or go to tutoring to ask about this part. But hopefully, this lesson help you understand like what a or connect probability distribution to something that we've talked about before, which is relative frequency. We're also reviewing a little bit about the range rule of thumb. We're also reviewing a little bit about probability that we talked about in chapter 4. So believe me when I say that everything in this class builds on itself, right? We're always reviewing old terms, old concepts, right? Thank you everybody for joining me, and I will see you next time.